These gold-plated towers are the state-of-the-art in quantum engineering. They're designed to suspend processors in environments colder than deep space, protecting fragile quantum states from the slightest thermal vibration. However, this chart reveals a massive scaling gap. To maintain 1,000 error-free logical qubits, roadmaps require 1 million physical qubits for correction. Building and cooling these pushes practical quantum computation past the year 2040. This delay persists because current designs attempt to solve quantum instability using the same logical habits that built the classical computer. The multi-billion-dollar industry is currently stalled by 3 specific classical inheritances that have proven incompatible with scaling quantum systems. The first limitation is binarity. We are trying to map the fluid, high-dimensional space of quantum states onto a rigid logic of zeros and ones. The second is planar geometry. We are still forcing quantum components onto the same flat, two-dimensional microchips used for decades in silicon electronics. The third is passive error correction. This strategy only detects an error after it occurs, attempting to fix the state after the wave function has already begun to collapse. Realizing the potential of quantum technology requires replacing these 3 historical habits with a framework designed for quantum reality. The first pillar of the ODTOE framework replaces the 2-state qubit with a 3-state Qutrit. This allows the processor to utilize 3 basis states, -1, 0, and +1. Mathematically, the most efficient base for any numeral system is Euler's number, roughly 2.718. This makes the integer 3 the absolute peak of information efficiency. This produces an exponentially larger computational space. At 100 components, Qutrits access significantly more basis states than qubits. These 3 levels already naturally exist in superconducting transmods. By moving to ternary logic, we simply stop suppressing the 3rd energy state and start using it for calculation. Aligning hardware with base 3 math reduces the required physical components by 37%, while providing built-in logical redundancy. The second pillar replaces the flat chip with a 3-dimensional toroidal, or donut-shaped network. On a flat grid, connecting distant points requires long swap chains. Every time information hops through a neighbor to reach its destination, the probability of a devastating error increases. In this phi-torus geometry, the ratio between the large and small radii is exactly the golden ratio, 1.618. This creates the shortest possible communication paths between all points in the network. The Kolmogorov-Arnold-Moser theorem confirms that tori with frequencies related by this specific irrational ratio are maximally stable. This golden ratio geometry prevents the computer's internal signals from resonating with environmental noise, physically insulating the quantum states from interference. The phi-torus uses fundamental geometry to ensure the system remains stable without relying on brute force shielding. The third pillar introduces active OO correction to replace the slow, reactive codes used today. The processor continuously monitors its own internal coherence. It detects the signature of an error the moment it begins to form. This is a hardware realization of Douglas Hofstadter's strange loop, a machine that acts as an observer of its own observation process. By adjusting feedback parameters in real time, the system effectively reverses the quantum arrow of time, neutralizing the error before the wave function collapses. This self-referential loop creates a computer that actively manages its own coherence throughout the entire calculation. These 3 pillars lead to a new understanding of decoherence. It is simply premature observation by the outside environment. Quantum computing is a race against time. The algorithm must finish its work and extract a result before the rest of the universe looks at the system and forces it to become definite. Qutrits, golden geometry, and self-referential loops work together to ensure the internal algorithm observes the result faster than the environment can destroy it. The ODTOE architecture allows the machine to outpace the universe's attempt to collapse the quantum state. This active protection relaxes the acceptable error threshold for individual gates from 1% to a more achievable 2%. Utilizing this design makes useful quantum computation a 5 to 10-year engineering project rather than a 20-year theoretical goal. By aligning hardware with fundamental geometry and ternary logic, we build systems capable of observing deeper into the field of all potential states.